Welcome to Solidio Gloria Physical Chemistry. This is the lecture series for quantum theory. This is third lecture, Schrödinger Equation for Harmonic Oscillator. So we are going to solve the Schrödinger Equation for Harmonic Oscillator, and the solution is based on the Hermite Differential Equation solver. So let's begin. Well, firstly, we'll just briefly review the mechanics of harmonic oscillator. There are two bodies, mass M1 and mass M2, connected by massless spring, and then this is a two-body problem, and the equation for body 1 and body 2, the equation of motion, ma, the acceleration times mass, is given by the force exerting on the body. And this problem can be reduced to center of mass and relative coordinate problem. So center of mass is separated by from the relative motion, and that relative motion could be represented to the infinite mass wall and the spring and the one body problem. So this reduced to one single body problem with reduced mass. Reduced mass mu is given in the relationship to M1 and M2. So actually it was 1 over M1 plus 1 over M2 is equal to 1 over mu. So that's the relation to obtain the reduced mass mu, and the relative motion is described by this equation of motion. Here we note that the angular velocity is square root of k over mu, and then the frequency is 1 over 2 pi times square root of k over mu. That's the frequency ni, okay? All right, and one more. And then actually the any motion is kind of moving, anything is moving under the potential energy. So potential energy for this vibration or the oscillation could be expressed in terms of the displacement, and actually this is expanded in terms of displacement. That displacement is from the distance from the L0, which is the equilibrium, the length or position. So L minus L0 is the displacement in this case. And then from where, from the energy of the, at the equilibrium distance or position. And this is the zeroth term, first order, second order, third order, and so forth. So first order term is the gradient times the displacement. Second order term is 1 over 2 factorial, actually 2, and then Hessian. That's the gradient. Let me use the laser pointer. Gradient Hessian, and then displacement square, and then 1 over 6 3 factorial. Third derivative and displacement cube, like that. And then if you look at this solid line, that's a normal behavior of diatomic molecule, let's say. And then we could see that the minimum of this potential energy, which is V of L0, let's set it to 0, and then the first term multiplied by the gradient, and here the gradient, the slope is 0, so this is also 0, and this was 0. And then the first term in this expansion is that actually the second order Hessian term, so 1/2 second derivative times the displacement square, and then and so on. So this Hessian has the name, which is actually the force constant. Okay, so 1/2 k the displacement square, and 6 gamma, the third derivative, displacement q, just like that. So harmonic motion, harmonic oscillation is just counting the second order term in displacement. Okay, so that is harmonic term, and the third order cubic term beyond is the anharmonic term. Okay, so this is how we look at the diatomic molecule with the harmonic oscillator approximation. Actually, I just went over the Hooke's law. The Hookean is that the force acting on the body or the spring is proportional to its displacement. So if the displacement is x, that is k, that is proportional to x, and then proportional constant is k. We call it force constant. Okay, so F equal minus kx, and then negative gradient potential is the force. So we have the negative sign for the force and then integrate it to obtain the potential energy. So potential energy for this harmonic oscillation is, if you integrate this with negative sign, then that's 1/2 of kx squared. So that's the harmonic potential energy. Okay, so we derived the Schrödinger equation in a way that there is a kinetic term, potential energy term, total energy is the Hamiltonian. So Hamiltonian operator has the kinetic energy term, which is kind of common, which is minus h bar square over 2m. Now we are using, instead of m, we are using the reduced mass, d square psi dx square. This is the kinetic energy term. Then there is a potential energy plus vx of x, v of x, and then psi of x. This is the Schrödinger equation, Hamiltonian side of Schrödinger equation, which is equal to energy times psi of x. So it's the general Schrödinger equation in one dimension. This is our harmonic oscillator. And then we have the potential 1/2 kx squared. So we put this here, and then we multiply both sides with minus 2 mu over h bar square, obtain this, and then we move this energy term to the left hand side, minus and positive, and positive plus times minus is minus. So we obtain this. So this is the equation, differential equation we are going to solve. So before we go further, we just will define this as alpha square. Okay, this alpha square, and then alpha square is this, and then you remember that there is a kind of omega, which is k over mu square root of it, and then ni is 1 over 2 pi square root of k over mu. Okay, so that you can have k in terms of 2 pi ni square of 2 pi ni times mi. So 2 pi mi square, ni square is 4 pi square ni square times mu, but there is another mu, and then over h bar square. Then you have alpha square root of this. So 2 pi ni mi over h bar, that's alpha. So kind of remember this, and then you will have figure out what's coming in later. Okay, so this is the differential equation you are going to solve. Before we jump into that, let's analyze a little bit detail of this. That's because we are going to get state function, the wave function should be well behaved. It is a state function kind of for this mechanical system. In order to be a state function, well behaving, and that has couple of some property. Continuous, its derivative is continuous and single valued, of course, and then it should be square integrable, meaning is that it does not have a singular point. It does not diverge. It should converge in all kind of domain. So when x goes to positive, negative, infinity, psi must converge. And then this term, if you look at this, x goes to infinity, x square goes to infinity, then you can kind of compare to alpha square x square. This can be ignored. Okay, but okay, so or because this is very small compared to that, so our differential equation reduced to this, and then you can solve this, and then that is solved in such a way that psi gives psi e to the minus alpha over 2 x square. Okay, so this is a kind of approximate solution. And then if you look at this, x goes to infinity plus minus, then this term goes to negative infinity, which means that we have a singular point at x positive plus minus infinity. So what we are going to do is to try a series solution that includes this e to the minus alpha x square over 2 and f of x. So psi, the solution to this Schrodinger equation of the harmonic oscillator, include this part plus fx. Well, okay, then we are going to express this equation in terms of the function f. So let's make a first derivative of this. Okay, first make a derivative of first part, leave the second part alone, and then leave the first part alone, and then make a derivative of the second part, just like this. And then we make another derivative of the first derivative to obtain the second derivative. And firstly we have to do 3 times. Make a derivative of this, leave alone of the 2, and make a derivative of this and leave the 2 alone, and then finally f prime. So 1, 2, third term. Okay, sorry, first, second, third. Okay, and then we do the same for this. So this time make a derivative of this, leave this alone, and then leave this alone and make a derivative of that. Kind of fourth and fifth term. And then all contains the e to the minus alpha x square over 2. So we have a common factor, and then kind of in the descending order of the derivatives. Now we put this psi second derivative here, and then have this together, and then we obtain this differential equation of f of x. Okay, now once we reached here, now we try a series solution. So f of x is expressed in terms of x to the nth power with the coefficient cn, okay, as a series. Okay, so first derivative of this fx is that cn n x n minus 1's power. Okay, second derivative is that cn n n minus 1 n n minus 1 cn x to the n minus 2's power. So this is the second derivative. Okay, for this one we have minus 2 alpha x, and first derivative n cn x to the n minus 1's power, but you had a x here, so this is x to the nth power. And then this is just a kind of constant to this, and then you have just fx like here. But note that this is x to the n minus second power, n minus 2's power, x to the nth power, x to the nth power. You can have this together, but you have to think about this a little bit more. And then, but note that when n equals 0, this term is 0. When equals n, this term is also 0. So it can run from n equals 2 and on. But if you substitute n with n plus 2, okay, so n plus 2, then this n is n plus 2, n minus 1 is n plus 1, x n minus 2, x to the n minus 2's power is x n's power. Then it can still run from n equals 0 to infinity. Okay, so you obtain this, but all three terms has x to the n's power. Then you can put all coefficients together, and that coefficient is identically 0. Okay, just like this. And then from here, from this coefficient, you can obtain the recursion formula. And then that recursion formula, Cn plus 2 is equal to just this and Cn, which means that if you have C1 equals 0, okay, C3, C5, all odd terms, coefficient 0. Then what you need is that just only C0 and C2 and C4, C6, just like that. Okay, so if C1 equals 0, then you have even ordered the terms only. So psi1 e to the, this was the factor, exponential factor in front of fx, so e to the minus alpha x squared over 2, and fx is a series solution. In this case, you have only even ordered term, so e to the minus alpha x squared over 2. Now it runs L 0 to infinity, but your coefficient is C12 x 12th power. Now if you put C0 equals 0, then you will have only odd numbered, odd powered term. This was even powered term. Okay, odd powered term only, so that you have e to the minus alpha x squared over 2, sigma L goes from 0 to infinity, C 12 plus 1, x 12 plus 1's power. So the general solution is a coefficient a times odd powered term times b plus b times even powered term. This is the general solution to the Schrödinger equation of the harmonic oscillator. Okay, now let's examine if our series solution behaves well. Well behaves. Okay. Before, in order to do that, we analyze the series, both series, actually the even ordered series and odd order series. So we compare the coefficient C12 plus 2 to C12. In this case, we compare C12 plus 3 to C12 plus 1. The ratio is this. For each case, L goes infinity. L is very large. Then you can put instead 12 plus 1, 12, 12 plus 2, 12, yes. And then ignore this, and you can put just the 4 alpha L. And this behaves, L goes infinity, it's just like alpha over L. And the same for odd powered term, alpha over L. Then, if the coefficient ratio is alpha over L, then see how it behaves as x goes to infinity or negative infinity. Before we do that, we can examine e to the alpha x square. This is actually e to the x series, which is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, like that. You remember the series formula? So you expand this in power series, obtain this. And 1 plus alpha x squared, alpha square x fourth power over 2, and so on. So we pick up two consecutive terms when L is large, and then compare it. then this coefficient divided by that coefficient will give you alpha over L plus 1. L is large, then which is alpha over L. Then these series behave the same. Okay, then this obviously diverge when x goes to infinity or negative infinity, which means that these two f1 f2 are also diverge, right? Because of this divergent, even if it eventually f1 f2 are multiplied by this exponential factor e to the minus alpha x squared over 2, but it ends up with e to the alpha, not negative, positive alpha x squared over 2. This also diverges. So whole psi diverges in this case. So that's because psi diverges. What we can do is, from this general solution, either A or B, set either A or B equal 0, and then truncate the other series to be finite, right? That's the way we do. So for this is the recursion formula. And then in order to truncate up to Cn term, and this must be 0, but then must be 0, then what we can have here is that energy relationship, energy that gives energy. So E, we can obtain E here as h squared over 2 mu 2n plus 1 alpha. Okay, now you remember what was alpha? What is alpha? Which is 2 pi mi over h bar. Now you kind of put this in together into n plus 1/2 h ni, right? So, but here the energy is given with a number. Well, actually this n is 0, 1, 2, 3, all integer numbers. So your energy is 1/2 h nu, 3/2 h nu, 5/2 h nu, just like that. So energy is quantized. The truncation, to make the wave function finite, you truncate it. The truncation gives you an integer number. That makes your energy quantized. So that is the quantum number. Now you have your energy indexed by the quantum number. Okay, so En in this case. And then also you name your wave function with the same quantum number, because it contains only that many truncated terms, and that's the different or unique wave function or solution to the Schrodinger equation of the harmonic oscillator. So this is your general solution. You either set A or B equal 0 and then truncate the series. So energy is given here, just we did that, and this is the recursion formula. And then what we do here is, well, actually there is a way you solve the Hermite differential equation and reach the general solution using Hermite polynomial. But here, for the pedagogical way, we will find psi 0, psi 1, psi 2, psi 3, and so on. Probably up to that. So the first, here we have E0, n equal 0, I'm sorry. Then E0 is 1/2 h nu. Then we will obtain psi 0 by this way. So psi 0, in this case, we'll say B equal, no, A equal 0. So we don't consider odd powered term. We consider only even powered term, but n equal 0, we truncate to C, up to C, we include only up to C0, then C2 equal 0. So that gives you energy this. So our wave function is only first term, C0 times e to the minus alpha x squared over 2. And C0 x0, which is 1, okay? And then you have to determine this C0. In order to do that, we utilize the normalization condition. So this is the kind of probability amplitude, and the probability is that amplitude square integrated the whole space. So integral minus negative to positive infinity psi 0 square dx, which is 1. I'm sorry, this is 1. Pen is not really that visible. And also that is 1. Okay. Okay. So this is constant, goes in front of the integral sign, and this squared, which is this, and then you can do this integral by memory. Well, we have done this many times. We drilled this in mathematics for physical chemistry or basic mathematics for chemistry in your freshman years. Okay, so this is just pi of alpha square root of that, and then that gives you that equals to 1, and then C0 is square root of alpha, alpha of pi to the 4th power, okay, because that's square and that is square root, okay. So you have C0, and then you put C0 here, and then this is your psi 0. You solve just as you solve the Schrodinger equation. Okay, so next, n equal 1. N equal 1, your energy is 3/2 of h nu, and then in this case B0 is 0, and then in this case you include only first term C1x, that's it. So C1x e to the exponential term, and then you normalize this, then you will obtain C1. So normalization is here, done here, and C1 square, and then that integral that could be done easily from your memory, and that's this, and then C1, obtain C1 from this normalization condition. This is the constant, normalization constant actually. So you obtain your psi 1 normalization x e to the minus alpha x square over 2. Okay, so what's next? N equal 2. Okay. So n equal 2 case, your energy is 5/2 h ni, and then psi 2. Now your A equals 0. This has to be determined, but you will include C0 and C2 term. Okay, so C0 and C2, C0 times 1 plus C2 plus x square and exponential factor. Okay, your C2 is determined from C1, C0 by this recursion formula, which is minus 2 alpha C0. So your normalization condition, this equals 0, this also need to be fixed. 1, this is 1. Yeah, this is 1. Okay, so this squared, everything squared, because this is squared, then expanded, and then you integrate it term by term, obtain this, and then you determine C0. If you determine C0, you can put here C0, that number, and also C2 from here, the relationship. Then that's how you determine, okay? So you obtain psi 2. Like this, you can go on. So determine psi 3, psi 4, like that. And we have done this, and you may do this, but eventually this could be ordered and put in a table, which actually you utilize Hermite polynomial. So Hermite polynomial is a function of alpha square root of alpha x. And in this case, we used the symbol Xi, and this is the polynomial, Hermite polynomial. In this case, psi 0 term is 1, and there is 1, okay? And psi 1 term, because it's psi 1, well, h1 actually, 2 Xi meaning is you have 2 alpha square root of alpha and x. So which is alpha goes here and then x is here. And then this include the normalization constant. So normalization constant is given here. So depending on this n, small n, you can obtain any psi n or En. En is easy because En is the n plus 1/2 h-ni. That's it. So n equal 1, n equal 0, n equal 0, n equal 1, n equal 2, n equal 3. Your energy is here, and then your wave functions here. So this, if you look at this, your harmonic oscillator wave function kind of has its most of the probability within the potential curve, which is 1/2 of kx squared. Some penetrate out of the potential curve. So this is just look like a harmonic oscillator wave function inside of the box. So inside meaning is the potential energy curve. So half wave, one wave, two halves wave, two wave, just like that. And then the probability, you find that oscillator inside of the potential well is to make square, or if this is a complex function, psi star psi. So that's the next slide. Okay, just like this. Okay, so this is the behavior. So this is the probability, meaning is that you this state of the wave functions, state of the oscillator, mostly within the classical limit. The classical limit is given by this potential curve, but there is a kind of tunneling out, or the probability beyond the classical limit. Okay, that could be analyzed further. But before that, we'll first examine if the harmonic oscillator, the solution for the harmonic oscillator or quantum harmonic oscillator fulfills the uncertainty principle. Well, firstly, we note that the lowest energy is not zero. We call that 0 point energy. The E0 equals to h-ni times half of h-ni. Okay, that is not zero. So that means that both p, momentum, and x, the position, cannot be determined to be zero simultaneously. Yeah, both cannot be zero at the same time. That's because in energy itself is the kinetic energy plus potential energy. So both of them could not be zero at the same time. Okay, that's kind of a manifestation of Heisenberg uncertainty principle, but we can check it. So we can calculate x average and x square average, and momentum average and momentum square average. Remember that once we have a wave function, for classical observable, there corresponds to what? Linear Hermitian operator. So position, the linear Hermitian operator is just x square, just x square. Momentum, the linear Hermitian operator is that this momentum operator, minus h bar ddx. P square minus h bar ddx is square. Okay, this is minus h bar square, d square dx square, like that. So once you have your wave function given, you can calculate this x average, x square average, p average, p x square average, expectation values. Those done, 0, ni plus 1/2 1 over alpha, 0, ni plus 1/2 h bar square alpha, just like that. This is reasonable because could be understood easily, because the position, minimum kind of average position is just in the middle, just like particle in a box. And momentum also, positive negative momentum, it cancels out, just like that. Well, actually the wave function itself is either odd function or even function. So in this case, even function times even function is even function, x is odd function. So any product include even, odd, that's odd function. Then is a symmetric integration range, that's 0, something like that. That kind of argument will give you x average equals 0, p average equals 0, and x square average this, p square average that, and then from these you obtain the variance of x, variance of p, which is this, okay, and then square root of that times square root of that. That determines the uncertainty in x and p, okay, this. So that is this value, okay, this times that square root, and then the lowest value, the smallest value of this is v in this, I'm sorry, usually we used to use n equals 0, which is 1/2 h bar. That's the smallest value. So sigma x, sigma p is equal to or greater than h bar over 2. That is what Heisenberg uncertainty principle dictates in this case. Okay, now we are going to talk about the tunneling effect. Okay, so we'll just look at this psi 0. You see this red part? That is the probability you can find beyond the classical limit. Classical limit is just here, given by the potential energy, okay, which is just the potential within the potential. So what is the question is that what is the probability beyond the classical limit? So, which means that probability exceeding the classical limit, and then you must integrate from negative infinity to this point of this function. Actually, square of this function, because this is the probability amplitude, square of it is the probability itself. And what I mean is that minus infinity to minus square root of alpha, 1 over square root of alpha, p dx. P is square of this one. And also from this point to the infinity, and this. And then these are the same because this is the kind of symmetric. We have just twice of that. And then put this function here and squared, of course. And then you obtain this. And then this is kind of known as the complementary error function, some number to the infinity. And we made it, substitute it in this complementary error function form. And then the lower limit is 1 to the infinity, okay? And this value could be obtained from the table or some computer-aided kind of a system, Mathematica, or I prefer you to use Python coding, and then you obtain this value, which is 0.16. So 60% is tunneling probability. So classically can never reach beyond the limit, but about 16% it can escape the potential one. This is the quantum effect. Okay, and also we can study diatomic molecule or chemical bond based on assuming that, of course, harmonic potential for the chemical bond. So we'll examine the vibration of diatomic molecules. Well, and then actually the frequency, fundamental vibrational frequency observed could be related to 1 over 2 pi times k square root of k over me, and also this is the wave number notation. So wave number is the reciprocal of wavelengths, okay, which is just to divide by this with the speed of light, and that will give you the wave number. Anyhow, from the experiment of H35Cl, the fundamental frequency is obtained, which is 2886 wave number. Now, you can obtain this K by square of this times square of this times me, right? The reduced mass, okay, just like this. And then you put these numbers together. 2 pi, C is here, and then fundamental frequency. But this is in reciprocal centimeter. In order to obtain Newton meter unit, we need to convert it to meter. So this is the conversion to meter. And then we obtain the reduced mass in AMU, but this is the conversion to AMU to kilogram. So all are in SI unit, and then you put numbers together, numerically figure out what the number is, which is 4.78 times 10 to the second kilogram per second square, which is about 478 Newton per meter. Okay, that's force constant. So that much is stiff, the HCl bond. Okay, there is another application. We want to know how, if there is a given bond distance, how much it fluctuates, how far it can extend or compress. Okay, so that could be done because once the fundamental frequency is known, you can compute the sigma x standard deviation, which was given, we figured out previously, h bar 4 pi c me fundamental frequency and everything square rooted. Okay, take a square root of it. So h bar here and 4 pi and c and fundamental frequency in meter, and then the reduced mass. Then make a square root. You obtain 7.67 picometer. HCl bond length is known to be 127.5 picometer. So about, let's say, 5% is a fluctuation of the bond. Okay. So this is the end of third lecture in quantum chemistry. Thank you.